So today we are going to talk about EMF, terminal potential, and internal resistance of a cell. Okay, these are terms you're already familiar with, and you've studied about these things in class 10 also. So just a bit of a recap for you all. Okay, so EMF is the work done to take a unit charge through the complete circuit. Okay, so we have a circuit in here, the external resistance being R, which is connected to a cell. All right. Now, any cell, we know any cell has something called an internal resistance. Okay, we will talk about this thing later. Okay, but the thing, these two components inside the dotted box makes up the cell. Okay, so these two things makes up the cell. So work done to take a unit charge to the complete circuit, that is both inside and outside the cell, is what is called EMF. So if we are to transfer a charge from one point in a circuit to any other point, you have to do work, of course. All right, a charge cannot run through this resistance, okay, on its own. So there has to be some energy supplied, and the energy is being supplied by a cell. So the work that is needed to be done to take a charge through the complete closed circuit, all right, okay, is what is called the EMF of the cell. Likewise, terminal potential, work done to take a unit charge to the external circuit only meaning that is only outside the cell. Okay, so the work done to take a charge from one point in a circuit to the other point, okay, both of the points being outside the cell, is what is called terminal potential. All right, work done to take a unit charge outside the cell or in the external circuit is what is called terminal potential. Now what we always see is, we see that the EMF is always greater than the terminal potential. This is always what we get to see. Okay, if you take a freshly manufactured cell, okay, say for example, this is the cell, okay, so this is the cell, and say for example the EMF is 1.5 volt. In any cell that you see, that you buy, okay, you will see its EMF value printed. Okay, so you check the EMF value, say for example it's 1.5 volts, and you take a voltmeter, and you measure its potential. You want to measure its EMF, say for example. Now the EMF that you will see of this particular cell will always be lesser than 1.5 volts, always be lesser than 1.5 volts, because what the voltmeter will be measuring is always the terminal voltage. It will not be able to measure, a voltmeter will not be able to measure the EMF of a cell, remember. Okay, it is always measuring the terminal voltage. So where is that extra potential gone? Okay, that extra potential, see, before we talk about that, see, both EMF and terminal potential are work done. They are work done. Both of these two things are work done. So, and work done basically is energy. So EMF and terminal potential, you can look at them as, some other form or kind of energy. They are basically energy, both of these two things. All right. So what happens actually is, there is work done to take the charge through the external circuit, which we are saying is terminal voltage. So you require energy, the energy that you need to spend to take a charge from one point to the other in the external circuit is terminal potential. But we need to do work to take the charge inside the cell also, because any cell will have something called its internal resistance. So we have to do work to take the charge through the internal circuit also. We have to spend energy to take the charge through the internal circuit also, through this internal resistance, that is. Okay, so there is some loss of energy over here. All right, so that loss in energy is what is called voltage drop or potential difference. Voltage drop or loss in potential. Okay, so it is because of this voltage drop, loss in potential, loss in energy, that the EMF is always greater than terminal voltage. Okay, and we see that the EMF is equal to IR. This is the potential in the outside circuit, this is the terminal potential, plus IR. This is I small r. This is the work, this is the energy, or this is the potential difference across the internal resistance. Okay, actually I should have shown you this first. E, the EMF, is the terminal potential, okay, plus the voltage drop, where V is the terminal potential and small v is the voltage drop or the loss in potential. There is always a loss in potential because of the presence of the internal resistance. Okay, now since we know capital V is I into capital R, that is R is the external resistance, okay, the voltage potential difference across the external resistance plus the potential difference across the internal resistance. Okay, so remember, it is because of this fact that the EMF is always greater than the terminal potential. I capital R is the terminal potential over here. All right. So therefore, from this equation, we can write, taking I common, R plus small r. So from here, we get I is E upon R plus R, that is small r. Okay. Now this, from this equation, let us call this equation number 1. So from this equation itself, we can write EMF is terminal potential plus the voltage drop. Okay, voltage drop is also referred to as back EMF, by the way. Okay, voltage drop is also called back EMF. Okay, so E is V plus I, the potential difference across the internal resistance. Okay, and you see the mathematics. We just want to get an expression for the internal resistance. So from here, internal resistance is E by E minus capital V divided by I. So R is this, because I is V upon R. Okay, so R is, the internal resistance is this much. Okay, check the calculation. Sometimes you might need it for doing numericals. Okay, by the way, you can get two expressions for the current. Current is EMF divided by the total resistance in the circuit. Current is EMF divided by the total resistance in the circuit. Or you can also write current is the terminal potential divided by the external resistance. The potential difference in the external circuit divided by the external resistance. So you have two expressions. You can write two expressions for the current. Remember that. Okay. Okay. So this is the expression for the internal resistance. Now, basically, what I want to discuss today is something called combination of cells. Okay, this is what I want to deal with in this video itself. So combination of cells, there are two ways. One is in series, the other is in, of course, parallel. Okay, forget about this picture. Yeah, I had drawn this, okay, but I forgot to draw the internal resistances in here. So that is why I've put a cross mark in here. Let us look at this picture. Although I have drawn, so this forms one cell, this is other cell, this is the third cell, remember. So although I have only shown 3 cells over here, you can have n number of cells. We are considering the n number of cells, whatever the number of n is, whatever n is. Okay, so we have cells connected in series, n number of cells, and we have capital R as the external resistance. So the total EMF, each cell, by the way, has EMF E. Okay, so the total EMF of the cells is, let us call that ET. Okay, not extraterrestrial, of course. Okay, a joke. So ET is summation of capital E, which is equal to N into E. Total internal resistance RT is summation of R. Since we have resistors in series, internal resistances in series, so we simply, since they are in series, we simply add up the resistances. Okay, so total internal resistance is RT, which is summation of R, which gives us NR, since there are n number of cells, NR. So what is the total resistance in this circuit? The total resistance in the circuit is NR plus capital R. Okay, this is the total resistance in the circuit. So therefore, what is the current flowing? Current flowing is the total EMF divided by the total resistance in the circuit. This expression. Current is the EMF divided by the total resistance in the circuit. Okay, now the total EMF in the circuit is NE divided by the total resistance is this. So this is the expression for the current. Okay, when we connect the cells in series. Okay, so yeah, I've rewritten the expression over here. I is NE by NR plus capital R. Now we can discuss two cases in here. We have connected the, don't forget, we have connected the cells in series, so we can discuss two cases in here. One case is if NR is much lesser than the external resistance. If the summation of the internal resistances, if the internal resistances are much lesser than the external resistance, so we can neglect this factor, okay, because this is very big compared to this. That is what we are saying. So we can write I is NE upon capital R. Okay, N or I is N times E by R. Okay, now what is E by R? E by R is the is approximately the current given by a single cell. Okay, say for example, we only had a single cell. Let me draw it over here. We only had a single cell whose EMF, of course, was E, and let us consider it had no internal resistance. That is what we are saying. We are eventually neglecting internal resistance over here. So it's like this cell has no internal resistance and this is the external resistance. So what is the current drawn? The current drawn is the EMF divided by the total resistance in the circuit. Okay, I hope you all are following, okay, what I'm saying. So if NR is much lesser than R, we have I is N into E by R, okay, where E by R is approximately the current given by a single cell. Okay, so what can we conclude? Therefore, total current is N times the current given by one cell. Okay, so current given is N times the current given by a single cell. So when we have cells connected in series and we get to see that the internal resistance is much lesser than the external resistance, so it is always beneficial, it is good to connect the cells in series, okay, to get a stronger current. Okay, so if the internal resistance is much smaller than the external resistance, then cells should be connected in series to get a strong current. Okay, and case number 2, if the internal resistance is greater than the external resistance, then what we do in this expression, we neglect this capital R, and thereby we get I is NE upon NR, which is eventually E by R. Okay, so the circuit is something like this now. So the total resistance, it's like the total resistance in the circuit is small r, because we are neglecting capital R. We are neglecting capital R. Okay, in this expression, we are neglecting capital R. So it's like in the whole circuit, the total resistance is R and EMF is E, of course. So what is the current given by the cell? The current given by the cell is E by R. So if NR is much greater than R, then we get I is NE by NR, okay, which is equal to E by R. So what do we conclude? Therefore, if NR is much greater than capital R and the cells are connected in series, we get to see that the total current is the same as the current given by a single cell. Okay, so that is why it is not suggested, okay, it is not advised to connect the cells in series if the internal resistance is much greater than the external resistance. It is not advised. Okay, we will see that if this is the case, it is beneficial in order to get a strong current. Okay, it is beneficial to, if this is the case, it is beneficial to connect the cells in parallel. We'll see that. Okay, so only when this is the case, when the internal resistance is much greater than the external resistance, when the internal resistance is much lesser than the external resistance, okay, only in that case we have to connect the cells in series. Now parallel combination will be something like this. We have n, this means dotted lines means there are n number of cells connected in series, parallel. Okay, so since the cells are connected in parallel, the potential difference between these 2 points, okay, will always be the same, which is E. The potential difference in parallel combination is the same, don't forget. So total EMF is E. So total internal resistance is given by now what? 1 upon RT. RT is the total internal resistance, the equivalent resistance in parallel, say for example. So 1 by RT will be given by 1 by R plus 1 by R up to n terms. All right. So this gives us, just a sec, this gives us what? This gives us here. So 1 upon RT is n upon R. Just check the calculation, n upon R. Because the LCM is R and you'll get 1, 1, 1 plus 1 plus 1 plus in the numerator. So therefore up to n terms it is. So this is n divided by R. So the effective resistance in parallel of internal resistance is R by n. Okay, I've drawn another picture for you all here also. So the total, so this is the total internal resistance, mind you. So what is the total resistance in the circuit? We have an external resistance also. The total resistance will be capital R plus small r by n. So current in the circuit will be how much? The EMF divided by the total resistance, okay, which can of course be rearranged and written this way: NE upon R small r plus n capital R. Okay, now again we have 2 cases. If the internal resistance is much lesser than R, then internal resistance is much lesser than R, then this thing can be neglected. Okay, so this current will be NE upon NR, so NN they divide each other, which is E by R. That is, the total current is the same as given by a single cell again now. we've already seen if this is the case, it is beneficial to connect the cells in series, remember. Okay, because when we connect them in parallel, when this is the case and we connect them in parallel, we see that the total current is the same as the current given by a single cell. Okay, so it is not at all advised to connect the cells in parallel if this is the case. So if that is what we've written, R is much lesser than capital R, then it's no use connecting the cells in parallel. And finally, case 2, if internal resistance is much greater than R. When this was the case, we have seen that it was no point connecting them in series. Okay, now this will be beneficial if we connect the cells in parallel. We'll see that. If the internal resistance is much greater than the external resistance, then in this expression we can neglect this. This term is neglected. So we have Ne upon small r. So current is Ne upon small r, so which is N times the current given by a single cell. Okay, so that is the current is nearly N times that given by a single cell. Okay, therefore if small r is much greater than capital R, then cells should be connected in parallel to get a strong current. Okay, I hope you all understood, although I went very fast. Okay, I discussed this very fast. Okay, recheck the video. If you didn't understand any problems you have, of course you have to let me know. Okay, take care, class 12.